Welcome to the introduction of the ICU4X project. We are proud to present the fruit of the brainstorm session that happened at Unicode Conference 43 last year. Today's agenda is as follows. We're going to introduce ourselves, describe the problem we are tackling, the project that is aiming at that, our upcoming release, a midterm plan, and then we will make ourselves available for a Q&A. In recognition of the ongoing global pandemic, we took the liberty to experiment with the virtual presentation by introducing more speakers than in-person talks usually do. We hope you'll enjoy this format as it allows us to bring experts from multiple fields to talk about their area of focus in ICU4X and conveys the wide range of experiences that back our effort. Let's begin with introducing ourselves. My name is Zibi Braniecki and I'm one of the lead engineers on the ICU4X project. ICU4X is a Unicode technical committee designated to work on a set of modular internationalization components suitable for use in a client-side and resource-constrained environments. At the moment, we have around 10 engineers involved in the project, mostly from Google and Mozilla, but we hope to attract more contributors and more organizations to our project as we make ICU4X an attractive platform to target. Our experts bring experience from Android internationalization, Fuchsia, Firefox, Clojure, and others. End of slide.
ICU project is based on Unicode standards and state-of-the-art libraries and specifications. We use CLDR as the best source of vetted i18n data, but library design allows for external sources and overrides. We use ICU4C and J as the starting point for both feature selection and implementation, and strive to be minimal in size and compatible in speed. Our API surface matches ECMA 402 specification for the best future coverage.
Hi, I'm Shane, and I'm the third co-chair of the ICU4X subcommittee. In addition, I serve on the ICU Technical Committee and TC39 Internationalization subcommittee, and I have given multiple talks and tutorials on ICU and ECMA 402 at this conference. The ICU4X subcommittee is part of the Unicode consortium, and we report to the ICU Technical Committee. Being part of the Unicode consortium enables us to work closely with ICU and CLDR development teams and build on the shoulders of giants. ICU4C and ICU4J have had over 20 years of open source development, and they are used in virtually all major software platforms in the world. Now we will go to the problems that we are solving with ICU4X. There are three main facets: scalability, on-demand data, and modularity.
The first goal is ability to scale to most programming languages, or write i18n logic once and use it everywhere. There is a large number of i18n libraries today of varying coverage and quality. Most complete are ICU4C and Java, supporting major languages like C++, Swift, Python, Java, and JVM-based languages. JavaScript support has improved drastically in past few years, but it's still somewhat fragmented. Some high-profile languages like PHP, Go, Haskell still have scarce i18n support. However, there are problems with patchwork of libraries. The most obvious is difficulty to scale. ICU4C and J each have over thousands of source files. Most of the other libraries implement a subset of functionality of those two. Even if you take time to port these libraries, the code and data get stale quickly. Another challenge with patchwork is unpredictable behavior. Many different implementations of core functionality like date and time formatting result in subtly different behavior based on differences in CLDR version, bugs in code, or different assumptions. Predictable behavior is important because it enables i18n to be performed in two different environments and get the same results. Websites using server-side rendering want the same behavior on client-side for live UI updates. Operating systems want consistent formatting across all apps. Polyfills and unit testing frameworks want to match the output of their reference implementation.
The second facet of the ICU4X problem statement involves the management of locale data. With ICU4X, we want to provide an end-to-end solution for your locale data. Last year, I gave a talk at this conference entitled Mastering Your ICU Locale Data. In ICU, we give you tooling to manually reduce your locale data bundle sizes. We also give you tooling to figure out what data you need to keep by using online tracing in ICU4C. However, those tools have their limitations. There is no static code analysis. The configurations must be written and maintained by hand. Even if you produce an optimally stripped data bundle, the ICU code itself is still too large for some consumers. Another challenge with ICU data is that you cannot share the same data bundle across ICU versions. Each ICU version needs its own data since the internal structure of the data is subject to change over time. I can say confidently that no low-hanging fruit remains in ICU data modularization. A project to fundamentally retool ICU's data pipeline would be a multi-year effort. The other big limitation is that ICU4C and ICU4J load data from a fixed data source shipped with the app. However, emerging client-side platforms like the web, mobile, and IoT are not monolithic. Being low-resource environments, they are foundationally built on the idea of include what you use. These platforms expect apps to load data from one of several types of services which I have listed here. However, when locale data comes from a service, apps may want to override certain keys to conform with brand requirements. ICU does not currently support data overlays. Another constraint is that modern apps are built to be responsive to changes in their underlying data. For example, an app may ship with a small number of locales and download additional language packs on demand. We need to think about how to update the app's UI to reflect data as it is loaded asynchronously.
The final facet is modularity. Internationalization domain is deeply interconnected, and any attempt to implement its components leads to surprising mesh of dependencies. For example, you may want to format a date, but the library will have you ship code and data to managing currencies, because that's what the number formatter uses, and well, dates and times have numbers. That was a result of organic growth of separate components into intertwined dependency over time. Mind you, each one of those decisions was reasonable at the time and made by smart people. The issue is that their goal was never to make things modular, and modularity is impossible to introduce retroactively. In many contexts, that trade-off is reasonable. Unicode ships a wonderful, all-encompassing set of solutions in form of ICU, CLDR, and Unicode. The main customers of those solutions are large desktop and server applications, GUI toolkits, and operating systems themselves. For those customers, bundling 30 or 50 megabytes of data to handle all their internationalization needs is not unreasonable. With more space, faster networks, and more memory, the budgets grow faster than the size of ICU and data. So even if the option was there, it would still likely make sense to ship the full set of components and all the data for all locales, rather than ask users of the code to navigate a network of missing APIs and missing resources. But at the same time, there is another trend. Computers are becoming introduced in forms and factors unheard of before, and software is being served over the wire. Google Performance Guidelines for Websites recommends the desktop website to fit all the necessary data under 1 megabyte, and for mobile, well under 170 kilobytes. Low-resource environments such as wearables become common with less than 512 megabytes of RAM, less than 500 megabytes of hard drive, and extremely low-powered CPU aiming to extend battery life. Many new users only need a core subset of ICU functionality and some of the data. They often need only a subset of locales to be available immediately, but would like to be able to load additional locales and additional data if needed. To recap, here are three main challenges that we see the need to address: scaling to new programming languages, local data management, and modularity. Now that we talked about challenges, let us introduce you to the project that aims to solve them. ICU4X is an effort to create a modern implementation of Unicode components in a performant language with ability to target many environments, flexible data management, and great modularization. We chose to prototype our solution in a modern programming language called Rust, because it is a low-level programming language with high-level ecosystem. It allows us to reach performance and memory utilization parity with C and C++, while enabling easy component management, package distribution, and FFI. Our goal is to distribute ICU4X in form of small components, such as ICU local, ICU plural rules, and so on, as well as a meta package called ICU4X. To achieve strong modularization, we are also going to use Rust features, which allow us to fine-tune reasonable defaults for best practices and good user experience, and allow developers to adjust how ICU4X works in their environment.
As you already know, there are many incomplete i18n solutions in the wild. Projects often fail to deliver on full feature set or fail in maintenance. One of our goals is to write business logic once and deploy it on different languages and platforms. Some ways of doing that are using WebAssembly, foreign function interface, and/or transpilation. Our current focus is on the first two. There are a number of WebAssembly runtimes available, but most important ones are in the browsers. There are problems with WebAssembly, which is made for apps, not libraries, but we are working with the core teams to overcome those problems. Foreign function interface, or FFI, is well defined, and it's already used with ICU4C, for example, in PyICU, and we're hoping it's going to be useful for Rust projects, which is able to export stable C interface.
Data provider is the other big piece of the puzzle. All locale-sensitive ICU4X APIs are built on top of data provider, an interface for on-demand locale data. In the future, the data provider architecture can also be used to ship other localized resources for your app, like message strings. I have two visualizations for the data provider. The first is this one, comparing a traditional service stack to the ICU4X stack. With a traditional service, the app interacts with the service through a thin HTTP client. Most of the complicated business logic happens on the remote server. However, with internationalization, it is infeasible to make requests to the server for every operation. For example, you may need to format a whole database full of dates and times. ICU4X sits between the app and the service. It downloads data from the service one bit at a time, and then uses it repeatedly to perform the business logic on device. We can scale this thanks to the WebAssembly and FFI approaches that Nebojsa discussed. Here is my second visualization. This shows how the programmer can combine multiple data sources into one data provider. In this example, there are three data sources: a JSON file, a cloud service, and an operating system RPC service. Each data source provides a different set of locales. Since the data sources all implement the data provider interface, they can be hooked together to power ICU4X. Combining data providers happens outside of the core ICU4X business logic. The data provider pipeline model also allows nodes to provide certain useful operations such as caching. The only requirement is that the node conform to the data provider protocol. Given ICU4X's goal of modularity, it's essential that we build an easy way to figure out what data your app needs. We can do this using static code analysis based on dead code elimination. ICU4X is thoroughly tested to ensure that you only get the data that you need to power the APIs that you are linking into your app. Another aspect of modularity is to reduce the amount of code that needs to run on device. By moving expensive business logic to compile time, we can make ICU4X smaller and faster for end users. Examples of pre-processing include compile time optimization of plural rules and the resolution of datetime skeletons.
In order to achieve write once, run everywhere, we need a strong test corpus that exercises different code paths available to run from any target environment, and preferably comparable between C, Java, Rust, and other target languages. In particular, strong corpus will allow us to verify that the output over FFI gets unified experience no matter if you launch it in Dart, JavaScript, WebAssembly, or Rust. Our goals are audacious, and we recognize how challenging the task is. We get to stand on the shoulders of giants like Unicode, ICU, CLDR, ECMA 402, and Rust, which allows us to focus on limitations of current systems rather than reinventing the wheel. But first, we need to validate our claims. How can we confirm that we indeed have the right model to address the issues? For the first couple releases, we have three drives. First, validate that we can develop a functional internationalization library that can be used in many environments. 2. Design the core architecture and implement the core shared components. And 3. Design a useful API based on the experience from ICU and ECMA402. Our upcoming 0.1 release aims to give us a very humble subset of what ICU can do, but hopefully enough to work with. The first component is local class. It's a core component for almost all operations. We needed to understand what data user wants, what data we have, and fallback between them. Every major API in ICU will need to pass a locale or a list of locales and retrieve data encoded in one, or a mix of them. In ICU4X 0.1, we include the first version of the component. It is purely algorithmic and handles parsing, simple operations on subtags and canonicalization of locale and language identifiers. While designing the API, we were aiming for a balance between full functionality of ICU, simplicity of ECMA402, all while trying to make it feel rusty. Unicode set is another low-level component, allowing us to select and operate on strings and list of characters. The way we design it provides efficient data structure for code points, is immutable, and uses a builder model for easy custom creation via mutation. For common properties, we will have static constructors functions, and we'll parse pp.ucd to get information. Pluralization is another one of the foundational pieces necessary for many higher-level internationalization components. In 0.1, we included CLDR data for cardinal and ordinal types and made the first use of data provider. The API is heavily inspired by ICU and ECMA402, once again looking to stay aligned with the Rust style guides.
Datetime format is our first high-level API, and at the same time, the most commonly requested API for internationalization. With it, we aim to design the typical formatter API with data management, string output management, constructor options, user preferences, and so on. In version 0.1, we implement the simplest subset, which allows the user to take a datetime and produce an output based on date and time styles. Notice the common use patterns that we'll see again and again in other formatters. A constructor that takes a data provider and some kind of parameters to customize the formatter, a format method returning a formatted datetime or a formatted value preserving field information, format to string returning a string, and format to write using an output stream. A very common way to create a datetime format is to specify a date and the time style. The styles are predefined values: full, long, medium, and short. If you ever used ICU or ECMAScript 402, this should be a very familiar pattern. This is an API that is proposed but not yet implemented for version 0.1. It allows fine control over the formatting while still being locale independent. This is very similar to JavaScript and should also be familiar from ICU if you think about skeletons. Last but not least, we are planning to implement a way to return a formatted value that still preserves information about every single field, where it starts and where it ends. The use case for this is that you can take the result and format the hour or the day of the month in a different style. The API for this is not even proposed. It's very early stage.
Beyond components, ICU relies on a high number of utility APIs that provide data wrangling, efficient storing, and handling of bits.
In our early release of ICU4X, we currently support loading data from JSON files. We have tooling in place to help you generate a tree of JSON files from CLDR. Soon, you will be able to load data that was statically linked at compile time and use bin code as an alternate machine-readable serialization format. For version 0.2, we will be launching an asynchronous data provider that loads from a web service.
In 0.1, we are already able to release each component as a standalone library that users can rely on, and as a meta crate that will allow users to get it all. Even when added as a meta crate, optional features, tree shaking, and other dead code elimination techniques allow us to efficiently cut out as much of the code and data as we can to keep the payload low.
ECMA 402 is an established and familiar client-side internationalization API. While the original API is implemented in JavaScript, the abstract API defined by ECMA 402 is a useful substrate for general internationalization use. So we defined an API surface in Rust inspired by ECMA 402, which we are implementing using the primitives provided by ICU4X. The traits can have other implementations as a polyfill for any missing functionality in the interim, such as the Rust ICU implementation, which is a Rust wrapper around the ICU4C library.
The next thing is documentation. One of the things we fell in love with in the Rust ecosystem is an excellent Rust doc and ecosystem around it. We see it as an opportunity to help people learn and use internationalization APIs properly. All of our public code can be easily documented in source, and all examples are also run as unit tests, guaranteeing that they will never get out of sync. It is very early for us to make any reliable claims about ICU4X performance, since we have so few components, and the only high-level component, datetime format, doesn't really handle advanced features like time zones or number formatting yet. But since we do aim to make ICU4X great target for embedding, web ecosystem, and FFI, we want to establish a culture of benchmarking early. At the moment, we aim to introduce 5 major metrics that we want to keep track of: performance, memory utilization, binary and data size, code coverage, and documentation completeness. All those benchmarks are preliminary and will change as we complete features and focus on improving our metrics. For performance, memory, and size, we recognize that ICU4C has over 20 years of optimizations on us. So initially, we just want to ensure that we are at least on par with them. We measure performance using the amazing statistical benchmarking tool called Criterion. It allows us to quickly compare any PR and evaluate it against the baseline. We recognize that our measurements are so far our wall times, which is a flaky measurement prone to error and noise. We're planning to improve the measurements to use numbers of instructions instead in the future. We also developed a simplistic harness with a small number of real-like applications to compare between ICU4C and ICU4X with an aim to reach parity. Please take those results that I'm going to show you with a grain of salt. Performance is hot, everyone loves to brag, but our goal here is to verify we're not regressing compared to C. Wins are nice, but this is not a goal yet. As you see, we used 3 sample files on a MacBook Pro 2017, and we verified that we get similar results on Linux. What you see on the screen is, in the performance column, is that ICU4X took around 300 microseconds less on creating 1,000 locale structs from strings. It took 8 microseconds less when matching them, and a full 1 millisecond less when serializing those 1,000 locales into strings. Similarly, in plural rules test, which selects a category for 10 plural rules in 10 locales for a total of 100, we see 200 microseconds improvement. And in the final test, datetime format, we see around 1.5 millisecond improvement when formatting 100 dates. With memory, we are really early. We are planning to hook up some instrumentation to measure peak memory. The only measurement we have is a microtask around storing a list of 1,000 locales, and we kind of believe that we have around 200 kilobytes savings there. Our initial worry was that size-wise, Rust will be less optimized than C++ is. Indeed, Rust sample executables without ICU are bigger than C++ ones, and once again we are very early in the process, so the results may be skewed. But we're glad to say that adding just ICU locale increases the binary file size less than adding ICU4C locale. For the plural rules sample, we add a little bit more, actually around 30 kilobytes more. And for datetime, we're adding much less, 1.8 megabytes less. But please remember that we'll need to carefully continue to measure that as we add more features to datetime format. We know it looks nice, but this slide is riddled with small print notes. The size difference wins are nice, but please remember that reference empty Rust binary is 200 kilobytes compared to 12 kilobytes in C++. So the fact that we're adding less doesn't really tell the whole story. Datetime performance is likely to further improve. We have a lot of low-hanging fruits, starting with the fact that what you saw is us reading JSON files. That performance numbers were with us reading JSON files in ICU4X, while in ICU4C we are reading binary resources. Very soon we are planning to switch our data provider to read binary resources, and we expect to see around 30% improvement on data read. There are many other performance optimizations in play, and we haven't really investigated binary size optimizations, but our targets are very aggressive. To compile ICU4X to JavaScript and be able to ship it in a web app, we'll need to make it much smaller than the current 200 kilobytes added for a date time. To recap, ICU is already fast. The fact that in some quasi-benchmarks we seem to be faster is nice, but we have no idea how it scales to real applications. We reason that we should end up being faster since we take all the ICU4C optimizations that Unicode came up with over the last 20 years and we add great performance-oriented solutions that Rust ecosystem developed. The real test for us will be when we will come up with the first client-side implementation and examples running, and the performance over FFI. Code coverage, at the moment, we're floating around 83% with an aim to reach 90% by 0.1 release. In reality, our code coverage is a little bit underrepresented because the code analysis tool is counting structs definition lines as uncovered line. So we're optimistic that we can hold high bar over time as we move more our test to data-driven. 2 crates so far have pretty good documentation coverage, while the rest is catching up. The tooling around documentation coverage is very young, but we hope to use it to maintain excellent documentation over time. 0.1 release is about setting the stage, the ICU in our name. Getting the first components, getting data provider, plugging it all together. 0.2 release is about the X in ICU4X name. We want to validate the data-driven testing concept, bring asynchronicity to data provider, and develop the first FFI to other languages like WebAssembly. In 2021, we'll continue adding features to make ICU4X a good backend for ECMA 4.2 specification. We'll develop FFI to run ICU4X for WebAssembly, Dart, JS, and others. We'll strengthen our data provider model to handle dynamic data loading and updates over app lifecycle. And we'll work on driving system requirements down. Our 0.1 release is imminent. 0.2 will come out early next year, and we hope to have a production quality code by summer next year. How many components and features we'll have by then vastly depend on our ability to attract contributors and organizations to the project. We started with a small core and employees from only 2 organizations. But today we introduce ICU4X 0.1 and invite you all to participate and contribute. If the vision we presented seems appealing for your needs and interests, consider dropping by our GitHub repository, try 0.1 out, and help us build the next generation internationalization components. And now we would like to invite you to a live Q&A with Nebojša, Shane, and I.